After this wonderful talk, I would like to invite Dr. R. Krishnan, an executive director and scientist at the Indian Institute of Tropical Meteorology, Pune. His research area includes climate modeling and analysis. This year, Sir has been awarded with MOES National Award. We heartfully congratulate you for the same. Needless to say, he has been awarded with many more prestigious fellowships and honors. Without further ado, I welcome Dr. Krishnan to take over this and talk about the contribution of Sukuro Manabe and Klaus Hasselmann for the physical modeling of Earth's climate, and quantifying variability and reliably predicting global warming. We welcome you, sir.
Yeah, yeah. Thank you very much, IISER Science Club, for this opportunity. Yeah. Uh, Let me share my screen. Screen. I need to share the entire screen, right?
Yes.
Yeah, right. Can you see this now?
Yes, sir, we can see.
Okay. Yeah. Yeah. Thank you, Science Club IISER, for inviting me to give this talk on the Physics Nobel Prize 2021 for the climate science contribution. And basically, just now we have heard a very nice talk by Professor Dhar uh, on the contributions of Professor Parisi. Um, so here, basically, I will focus on the work of Professor Sukuro Manabe, and to some extent about Klaus Hasselmann, who shared both of whom who shared the Nobel Prize for Physics for the climate science contribution. As actually this was read out in the citation by Professor Dhar, that the scientific background on this Nobel Prize in Physics for 2021 is for groundbreaking contributions to our understanding of complex physical systems. So, Professor Manabe and Hasselmann, Klaus Hasselmann, they share the prize for the physical modeling of the Earth's climate, quantifying variability and predicting and reliably predicting global warming. And the Professor Parisi for the discovery of interplay of disorder and fluctuations in physical systems and from atomic to planetary scales. Basically, both this the commonality is the complex physical system, and the climate system is also a complex system. It has interactions across different components of the climate: the atmosphere, the ocean, the land, the biosphere, and the cryosphere. They're different, and there are multiple scales involved, scales of interaction. So if we want to really climate change or predict global warming, we really have to understand this, quantify these interactions. And when you deal with a actual climate, it's very, very complex. And so it's very important to understand, simplify this whole process and provide a very simple picture of how the climate will change, for example, due to the doubling of carbon dioxide. And for understanding the climate change and in a complex system, the simplicity of modeling is very, very important. And this is what Manabe understood, and also the same thing Klaus Hasselmann also. So they all developed very simple conceptual models for the physical modeling of the Earth's climate and quantifying variability and reliably predicting global warming. And Professor Manabe, the climate model, basically, he was the first researcher to explore the interaction between radiation balance and the vertical transport of air masses due to convection. So this was in 1960s, 1950 and 1960s. People did not know how to represent convection in atmospheric models, how the heat is transported upward, how the moisture, humidity, momentum is transported by convection, how to represent them in models. So I think he made the first, this was his most important contribution. And he developed very simple model known as the radiative convective model. I will be discussing about this. And this is very important. The development of this radiative convective model is very important in understanding what will happen if, for example, the carbon dioxide in the atmosphere is increased. Because we know that the solar radiation, which is very most fundamental driver of the climate, almost 70%, the atmosphere is transparent. The Earth's atmosphere, almost 70% of the solar radiation it passes through the atmosphere because it's transparent to it. About 30% is reflected. And this incoming solar radiation, which enters the atmosphere and hits the land surface, reaches the land surface and the ocean surface, it is absorbed, and the Earth atmosphere system emits in the infrared radiation. And the infrared radiation is basically trapped by the some of the gases known as the greenhouse gases, like the carbon dioxide and water vapor. The water vapor is the most dominant greenhouse gas, also methane and other greenhouse gases. So, and this is what makes life possible. So it keeps the, because of the absorption of this long wave radiation by these trace gases, which are in small quantity, and they re-radiate back the radiation to the earth, they maintain a warm temperature. So without these gases, the temperature of the planet would have been very, very cold. So, so the greenhouse gases are very important. Now, and basically, in addition to that, when the solar radiation heats the surface, it also leads to development of convection. The air masses that are going to rise, they are lighter because hot air is lighter compared to the cold air, and it rises. And if it has moisture also, as the water vapor, as the air rises, it enters lower regions of lower pressure, so it has to expand. So if it expands and if there is water vapor in the parcel, the water vapor can condense. So if it is and once it condenses, it's going to release latent heat. So the moment you introduce moisture, you're bringing a whole deal of complexity into the system. So how to represent this convection and radiation interaction and how it influences climate? So Manabe and Weatherall, they developed a very simple one-dimensional model uh, for representing this radiative convective transfer. And I will be describing that in my presentation, subsequent slides. And Klaus Hasselmann, so the question is, when we are talking about weather, it's a very, very chaotic system. Uh, and and this is a very fast varying system in the atmosphere. The weather is rapidly changing, and now, but the climate is like a, it's like a flywheel. It has a inertia. It evolves very slowly. Now the question is, when we are talking about some external forcing, like let us say carbon dioxide, it is trying to change the climate. The question is, how do we detect it amidst so much of chaotic signal? How do you separate out the signal uh, in a complex climate system? So basically, Klausman developed simple stochastic climate models. I will be discussing that in my talk, and developed various methods to distinguish between natural and human causes. That is basically known as the fingerprints of atmospheric heating. And this methodology, the contributions that he did with simple models were later on, uh, they provided the fundamental basis for developing detection attribution techniques of human induced climate change, which we use in the IPCC. And this is an example which shows that the black line is the observed temperature, right, starting from the 1900 to the present. And the red line shows this is for the global mean temperature of the experiments from multiple models, um, which includes natural forcing as well as anthropogenic, that is human caused forces like greenhouse gases, aerosols, land use changes, and so on. And so when you see the global mean temperature in the last century, since 1900, it has warmed by about the global mean temperature has increased by 1.1 degree. Now the question is, how do we know that this is due to human activities? Can we attribute? Now these models are now clearly showing that this trend, observed trend in the global mean temperature by 1.1 degree, can be explained only when you include this anthropogenic drivers like the greenhouse gases and aerosols and other drivers. But if you had only natural forcing, like for example the volcanic eruptions, these big eruptions, they throw a lot of sulfate aerosols, and once these eruptions are very strong, very massive eruptions, these particulate matter can enter the stratosphere, that is above the troposphere. And once they enter the stratosphere, they can leave, I mean, they reside there for a few years. And the property of these aerosols like the sulfate is to scatter the incoming solar radiation. So once the aerosols get into the stratosphere, they can reflect, they can scatter the incoming solar radiation, and they can cool the planet. But these are very episodic events. These volcanic events are natural events, they are very episodic. And these models, the climate models, you can see this is the famous 1992 Pinatubo eruption. You can see the models are able to capture the cooling, and also the El Chichan, that was another big eruption. So these eruptions can also, these are natural forces. They can also affect the global climate, but for a short period of time. But if you want to really explain this long-term trend, increasing trend in the global mean temperature, now we are able to clearly attribute this because of the human influence, primarily due to the greenhouse gas concentrations, increases in the atmospheric greenhouse gas concentration, carbon dioxide, and also methane, and and partly due to, and there's also some cooling due to anthropogenic aerosols. I'll come to that in my subsequent slides. Uh, so identifying the fingerprints, I think the fundamentals of identifying the fingerprints was laid by Klaus Hasselmann. He provided the basic theory for that. And I was very lucky, extremely lucky, to have an opportunity to work with Professor Suki Manabe for 2 years in Japan. And so I would like to first of all pay my tribute to him. He is a great legend. I would rate him as the most outstanding climate modeler the world has produced, and probably the father of climate modeling, we can say. And he is a climate scientist par excellence. He pioneered physical modeling of Earth's climate and global climate change research. And he was the person who created and led a world-class climate modeling group at the Geophysical Fluid Dynamics Lab, Princeton, USA. And and he made several, not just he made several contributions, and each one was he was almost a first in everything, making the landmark contributions on a wide range of topics. Of course, I'll be touching upon is how we the elucidation of the atmosphere radiative convective equilibrium with positive feedback effect of water vapor. This is the famous paper by Manabe and Weatherald in 1967 that got the Nobel Prize. And he also developed three-dimensional models of the atmosphere with for climate studies. He also quantified the effect of increasing atmospheric carbon dioxide on the Earth's climate. And he was also the first person, he simulated for the first time the three-dimensional response of temperature and the water cycle, what we call as the hydrological cycle, to increased carbon dioxide. And he provided the first simulations of the climate by a coupled model, by an ocean atmosphere coupled model, not just an atmospheric model, but this is through coupling of a ocean model and atmosphere model, because normally the ocean model has a slower time scale, it evolves much more slowly. And this is in 1969 with Kirk Bryan. So they developed the first ocean atmosphere coupled model. And he has also produced important contributions on modeling the South Asian monsoon, the Indian monsoon. And he also studied the effects of orography on climates, how orographic barriers like the Himalayas, the Tibetan Plateau, Rockies, and the Andes, how these orography can influence climate in different regions of the world. And he also studied the effect. He was the first person to develop a model of soil moisture and land surface processes. This is something known as a bucket model, a simple bucket model, and how to represent that, and what is its effect of land surface process and soil moisture on the climate. He also modeled the influence of ocean atmosphere coupled variability. So when there's a coupled interaction between the ocean and atmosphere, it leads to climatic variations on different time scale. So that also he investigated. And also more importantly, because the carbon dioxide has been steadily increasing in the atmosphere, before the pre-industrial period, the atmospheric carbon dioxide concentration was something like 270 parts per million by volume. Now we have increased very rapidly during this last 150 200 years. We are touching 415 parts per million by volume. It's a very rapid increase, mostly due to the human activities, largely coming from the anthropogenic activities. And so he investigated the time dependent, how if you keep changing the carbon dioxide in the and the greenhouse gases in the atmosphere, how the time dependent response will behave. And he also studied different problems on past climate change, because I heard just now Professor Dhar mentioning about slow climatic changes happening on associated with the glacials and interglacials, which they can find from this delta 18 O, the oxygen isotope records from the deep ocean sediments. So people have observed climatic changes going back to uh, hundreds of thousands of years from these proxy records. And he modeled those climatic changes, including the ice ages in the past. And he also, one of the important problems, he studied the impact of freshwater input, because in the North Atlantic Ocean, you have a lot of ice cover and also ice sheet, especially the Greenland ice sheet. So a lot of ice is there in the polar regions. So with increasing temperatures, this ice is going to melt. And so you are going to add more heat and also more fresh water in the North Atlantic. And if this happens, it can really affect the deep ocean circulation, and it can lead to abrupt climate change. So he also investigated these problems and many more. I will not be able to cover all these topics. So I thought during this presentation, I will just focus on his Nobel Prize winning work. And Professor Manabe, he always emphasized on understanding the climatic phenomena. He told the most important thing is you have to really understand, make it very, very simple, and any complex process. Otherwise, we will not be able to predict it or explain why this is happening. So understanding the climatic phenomena is very important. And what are the physical processes of variability and change? And it should be very simple, clear, and very practical, quantitative and straightforward. And he always believed in logical and deductive reasoning. You have to deduce step by step, go step by step, one at a time. And so that was his strategy. And sorry, just a minute. And he was a very inspiring person with positive energy and full of enthusiasm, and always very cheerful and inspiring person. He guided and mentored generations of climate scientists across the globe, including several Indian scientists. So truly a great legend and an amazing scientist. And he's been one of my heroes, I would say. Uh, so this is a brief introduction, and a great human being too. So this is Professor Suki Manabe. Let me go to his, yeah. So before I go to the into the contribution of Professor Manabe, I thought to keep the, of course, the audience may be familiar, but I thought I should provide a brief historical perspective of the problem, why it's so important. And if you go back to the origins, the numerical weather prediction, how to predict weather using numerical models, these ideas were developed. We call it as NWP. They started more than a century ago in 1904 by Bjerknes, a Norwegian scientist. So he had proposed at that time that weather prediction should be based on well-established laws of physics, all the Navier-Stokes equation, the conservation laws for the mass, and the also you have the water vapor equation and the thermodynamic energy equation. So if you have all these well established laws of physics, and you should be able to predict weather if you know the initial condition, initial state of the atmosphere. And he regarded this as a deterministic problem. So if you know the initial state accurately, sufficiently accurate, you should be able to predict the future states. And subsequently, L.F. Richardson, this is during World War I in 1922. He's from UK. He was from UK. He attempted to solve these equations numerically. At those days, there was no computers, were not there, by hand. And but his solution was actually turned out to be a failure. But it actually led to other big discoveries. L.F. Richardson's failure. And over a period of time, several obstacles had to be overcome. A fuller understanding of the atmospheric dynamics took place. And also, there were these regular radio sondes, balloons, which were taking routine measurements of the atmospheric profile of temperature, water vapor, wind speed, wind direction. And later on, satellites came in this 60s and 70s. So we could have, because these observations, they provided the initial conditions for all these numerical models. And then people also developed very stable finite difference schemes, because if you want to solve these weather prediction models, it has millions of computations. And so normally we employ the traditional finite difference method to solve these differential equations. And and then by in the 1940s, the first computer came, the what is known as the ENIAC, the electronic numerical integrator and computer at the Pennsylvania University of Pennsylvania. And then a very important contribution came by Jules Charny, von Neumann, and Fjordhoft. They had a numerical integration of a barotropic vorticity equation. This is at a single level. You have the how these vortices, how these low pressure and high pressure systems, how they evolve. And they had developed a theory known as the quasi-geostrophic approximation and hydrostatic balance. And this was very important for eliminating acoustic and gravity waves, because normally these waves grow very fast, and the acoustic and gravity, these are very fast growing waves. And if you have small errors in your initial condition, so these fast growing waves will lead to spurious waves that can grow rapidly, and their forecast is going to go bad. And this is the problem that was happening to Richardson. He did not know how to eliminate the gravity waves. So this development of this quasi-geostrophic approximation and hydrostatic balance, Charney and team, they could eliminate the acoustic and gravity waves, but they could retain only the large planetary waves, which is important for the weather. So the first numerical model of the atmosphere was there. This was in 1950, and subsequently Rossby and team, they made the first real-time weather forecast in 1950. And the first general circulation model of the atmosphere was developed by Norman Phillips. This was 1956. He did a numerical experiment, and he could demonstrate monthly and seasonal pattern of circulation in the troposphere. And this was the beginning of the general circulation models and climate models. And later on, from here, the GFDL, Princeton, where Professor Manbe, they took over the geophysical fluid dynamics lab. This was the beginning of the climate models. By then, also an important development had taken place. Edward Lorenz from MIT, he had determined he had discovered deterministic chaos. So he proposed that he has used a very simple model of convection, of atmospheric convection. It has only three variables, and it was a nonlinear system, and it exhibited two regimes with chaotic transition between them. So he argued that even if you have a perfect model with a deterministic model and almost perfect initial conditions, that means you have slight perturbations, slight differences in the initial condition, then the forecast will lose its skill in a finite amount of time. So it is like saying that if there's a butterfly flap in Brazil, it can change the forecast in Texas in 1 or 2 weeks, 1 or 2 weeks. So he said there is a limit to predictability of weather. You can't predict weather beyond a certain point of time. And this was the chaos, the theory of chaos that came from Lawrence. Now, at this point of time, people started investigating how to model climate. So we have to really understand. So the question is, when you are not able to predict weather beyond a few days, how can you predict climate, and how can you predict climate change? So normally, so when you say I'm going to increase the carbon dioxide and say this is what is going to happen to the global mean temperature. The question arises that, see, weather is highly unpredictable. How are you going to separate? There is so much of noise, so much of internal variability. And so when you so how do you separate, how do you say that this is the human contribution? So this is where the contributions of Manbe and Hasselman come, where they were able to, with simple models, they were able to separate how they showed that how climate can be modeled, and how external forcing like carbon dioxide or human influence can be studied with these models, and how to detect those signals due to anthropogenic forcing and separate it from the natural variations. And meanwhile, powerful electronic computers developed over a period of time. And now we have massive increase in supercomputing power, in the computing power. So this is the, so I thought that was the introduction for weather prediction. But people, they're also looking at climate, because weather is what you get, and climate is what you expect. So it's basically a mean, or weather is basically, the climate is basically a mean over a long period of time. And people were looking at climate, and about nearly 200 years back, Joseph Fourier had was trying to examine the balance between the incoming solar radiation and the outgoing long wave infrared radiation from the earth. And he said that there must be, the atmosphere must be trapping the long wave radiation. He had conjectured that, so it must be trapping the long wave radiation radiated by the earth, and this is important for maintaining the temperature of the planet. This was more than 200 years ago. This is known as the glass bowl effect. And later on, John Tyndall, this was 1859, he demonstrates and explains the physical basis of what we now call as the greenhouse effect. That is, the atmosphere admits the entrance of the solar heat, that is the solar radiation, but checks its exit, and the result is a tendency to accumulate heat and heat the surface of the planet. And then Svante Arrhenius is a Swedish scientist, and it was in 1896 he tried to understand what may happen if the carbon dioxide, which is a greenhouse gas, if you double it. He was also a chemist, Svante Arrhenius. If you double the carbon dioxide, what will happen to the surface temperature? And he estimated it was around 5 degrees, 5 to 6 degrees from his rough calculations, because he was only looking at the effect of the radiation, and he did not include water vapor. He did not have convection. I'll come to that. And later on, Guy Callender, this was in 1938, he states that human activities have led to increased surface temperatures. And by Charles, in the 50s, Charles Keeling, uh, he had set up a facility first at the Scripps Institute of Oceanography to measure the concentration of greenhouse gases like carbon dioxide and methane. And later on, this was shifted to an observatory in Mauna Loa. And now they have been making long-term measurements of carbon dioxide, because it has to be done in a very pristine environment, because it should not be contaminated by local sources. So and carbon dioxide is a long-lived gas. It's a well-mixed gas, greenhouse gas in the atmosphere. It has a very long lifetime of 200 years or so. And once you inject into the atmosphere, it stays there for a long time. And if you want, so you have to measure these changes. And if you want to monitor carbon dioxide, you need a very pristine environment. So this was started by Charles Keeling. Now, the increases in the carbon dioxide concentration from the 50s to the present, it is known as the Keeling curve. And there is strong evidence that has increased very rapidly during the last few since the 1950s, especially. And but two important papers by Manbe and Strickler. This was in 1964. They tried to look at the thermal equilibrium of the atmosphere with a convective adjustment. So this was the first time they developed radiative convective models, one-dimensional models, to compute the states of thermal equilibrium, as well as thermal equilibrium, basically both radiative and convective equilibrium, as well as pure radiative equilibrium of the atmosphere. And later on, this idea, using this radiative convective model, Manbe and Weatherall, this is the famous Nobel Prize winning work of 1967, they examined the thermal equilibrium of our atmosphere with a given distribution of relative humidity. They fixed relative humidity. And this was one of the very smartest and very clever, most clever approximation. And and they also did an experiment that by where they increased the carbon dioxide content in the atmosphere, and also another experiment where they decreased the carbon dioxide concentration to half of its value. And so with fixed relative humidity, what they found was if you increase the carbon dioxide, if you double it, the temperature increases of the planet increase, surface temperature increases by 2.3 degrees. And whereas if you use, if you half it, if you make the concentration half, it changes by 1.3 degrees, and by about 1.3 with, and and this was the first clear demonstration of the water vapor feedback. They said that once you increase, once the temperature increases, in the surface temperature increases, there is going to be more evaporation, more water vapor in the in the atmosphere, and water vapor is also a greenhouse gas, and that can further amplify the warming. So this is known as the water vapor feedback. This is the first time they demonstrated. So basically, as I said earlier, you need the greenhouse gases, the layer of the atmosphere, to maintain the temperature of the planet at mean temperature at around 15 degree global mean temperature, at 15 degrees centigrade or 288 degree Kelvin. So if these gases were not there, we would have a much cooler atmosphere. The temperature of the planet would be much lower. It would be something like minus 18 degrees centigrade, and practically life would not be there. It would be an ice ball. And this estimation you can do with a simple balance between the incoming energy, solar and radiation, and the outgoing energy by the planet. And you do this simple calculation by assuming that with the assumption that the measured albedo of the planet is about 30%. So you can estimate this temperature without the atmosphere, it would have been much cooler. And basically, with the due to the presence of the thin layer of the atmosphere, we are having this greenhouse effect, which keeps it warmer. It warms by about 33 degrees and keeps the mean temperature of the planet at around 15 degrees, which has now increased, of course, due to the increasing carbon dioxide concentration. So so you need the atmosphere. So the atmosphere is going to determine the surface temperature. In addition, the vertical variation of the temperature in the atmosphere, it is going to determine how the temperature varies in the vertical, is going to determine how the outgoing radiation at the top of the atmosphere is very much dependent on the vertical variation of the temperature. This I will come in my subsequent talks. So this is a very interesting article by Piers Foster from the University of Leeds. He said this is the Manbe, and this is the most influential climate science paper of all time, the thermal equilibrium of the atmosphere with fixed relative humidity by Manbe and Weatherald. And this is a picture of Manbe in the 70s with Professor Joseph Smegoronsky. He was the founding director of GFDL and another big legend. And this is a picture in 1970s. And basically what Manbe did was he modeled the links between the temperature, altitude, and carbon dioxide levels. Uh, this I have again taken from the Swedish Academy of Sciences. And what they did was, what they noted was they did this temperature at the surface is fell by 2.28 degree when the level of carbon dioxide was half. That means when you decrease the temperature from the 300 parts per million by volume to 150 parts per million by volume, the temperature of surface temperature decreased by 2.28 degrees, but it increased by 2.36 degrees when the level of carbon dioxide was doubled. This is, of course, they have zoomed it here. This is the vertical variation of the temperature for the three experiments. You have the control experiment, you have the experiment where the carbon dioxide is made half, and this is the experiment where it was doubled. So in the troposphere normally the temperature decreases with height because the radiation is emitted by the earth and it decreases with height. And in the stratosphere, the temperature actually increases with height, because in this region there is an absorption of the incoming solar radiation by ozone. And so normally, and also there is an emissivity at the top of the atmosphere. These factors are going to determine the way the temperature varies with height in the stratosphere. And now if you see, what they did was, as you increase the carbon dioxide, when you double it, not only the surface temperature increases, also the troposphere warms, the whole troposphere, that is the red line. But but in the stratosphere, the rate of increase of temperature with height is lesser in the double CO2 experiment as compared to the control experiment. That means the warming in the stratosphere, basically the stratosphere is relatively cooler with height compared to the control experiment. So this is an important point that they noted. So if it was due to increased solar radiation, the entire atmosphere would have warmed. This was his main point. I'll come to this. And this is a brief history I picked up from that article by Pierce Foster. After the Second World War, many of the Japan's smartest scientists found jobs in North American laboratories. Suki Manabe was one of them. A 27-year-old physicist was part of this brain drain. He was working on weather forecasting but left Japan in 1958 to join a new research project by the US Weather Service to develop a numerical model that could be used to study climate. So at that time, now they're trying to study climate. They're going beyond weather and working alongside Joseph Smegoronsky, the GFDL's visionary first director. Manabe led a team of computer programmers to add missing physics to the lab's weather model. Even the best computers in the world at that time were far less powerful than today's mobile phones. So, to get the model to work, Manabe needed to make the physics as simple as possible. This was his plan, that you really need to make your physics very, very simple. This meant making a range of coding approximations to quantify how the air exchange heat and water vapor with the land, ocean, and atmosphere. So, in trying to simplify the code, Manabe and his colleague Richard Weatherall wanted to know the minimum number of discrete levels. They were asking very simple questions. How many vertical levels do I need to use in the model atmosphere? And what greenhouse gases should I use? Should I include to adequately represent the way temperatures vary with altitude? As these gases absorb heat emitted by the Earth's surface, but at different levels. So the three-dimensional computer, and by that time, mind you, they had already developed a more computer-intensive model, a three-dimensional model, but that was more computationally intensive. So they had to build a simpler one-dimensional model to understand how the radiation and convection and clouds, how they interact to distribute heat and water vapor through the atmosphere. So they wanted to really simplify and have a simple one-dimensional model. And basically, this Banabe and Weatherall paper, the bulk of this paper concerns itself with building a simple model and doing these tests. But they also do two other experiments in the paper to quantify how greenhouse gases might alter climate. And this is where the breakthrough occurred. They found that they had built the perfect model to accurately estimate how human activities could alter Earth's surface temperature. Their first such climate change experiment was not to look at the role of carbon dioxide. That was not the really aim, but was to look at the effect of water vapor injected high into the stratosphere from a potential fleet of supersonic jets. They are referring to deep convection. When this deep convection happens, it's like a supersonic jet of water vapor getting into the stratosphere. As this and also a possible nuclear winter were the immediate concerns of that time. However, the table 5 goes down in history as the first robust estimate of how much the world would warm if carbon dioxide concentrations doubled. Manabe and Vadaral estimated 2.36 degrees of warming. Mind you, Swant Arrhenius' estimate was about 5 to 6 degrees. They told this warming is around 2.36 degrees, not far from today's best estimate of 3 degrees, even from the best models that we have today. And this is a simple description of the paper by Manbe and Mudral. They looked at the radiative convective equilibrium of the atmosphere with a given distribution of relative humidity, which they fixed, is computed as an asymptotic state of an initial value problem. The result shows that it takes twice as long to reach a radiative convective equilibrium. So if you have both radiation and convection, the thermal equilibrium will take twice as long. That means it will be much slower for the atmosphere with a given distribution of relative humidity than for atmosphere with a given distribution of absolute humidity. I will come to this. This is a very important point. Also, the this surface equilibrium temperature of the former is almost twice as sensitive to change in various factors such as solar constant, carbon dioxide content, ozone, cloudiness, and so on. So, relative to the adjustment of than that of the later. So if you have if you are having fixed relative humidity, your surface temperature response is twice as sensitive as compared to the fixed absolute humidity. And that is one more point. And according to our estimate, a doubling of carbon dioxide in the content in the atmosphere has the effect of raising the temperature of the atmosphere, uh, whose relative humidity is fixed by about 2 degrees. And earlier there was a study by Moeller et al. They had argued that if you use uh, fixed relative humidity, there would be extreme sensitivity of atmospheric temperature. But Moeller was basically using the relative humidity at the surface. That was the difference. And the idea of the logic behind the use of fixed relative humidity in the atmosphere, this was a very important approximation they did. Their argument was, even when you take the change in the look at the vertical distribution of relative humidity with height, even between two seasons when the temperatures are far apart between the summer and winter, the relative humidity doesn't change much. And this gave them the idea that we should go with the relative humidity with height. And I will come to this. And now this is just to give you an idea. So absolute humidity is basically, we are talking about the mass of water vapor per unit of air. So it is a density, and basically it depends on the volume of air. But if you take relative humidity, it is basically a ratio of the vapor pressure by the saturation vapor pressure. And this depends only on temperature. So they were, in a very clever way, in a way, they said that if we go with the relative humidity, it depends only on the temperature. And so this was a very clever idea. And they also did this, what they developed with this one-dimensional model was they compute temperatures at different levels in the atmosphere. They had a 18 level model and also a 9 level model. It's a one-dimensional model. And this I, basically this T at I is the temperature at level I, and tau plus 1 is the time T plus 1. So the temperature at time tau plus 1 is equal to the temperature at time tau plus HA, the computation of temperature change due to radiation, which they compute how much it changes due to the radiation and the convection change. And they had a way of adjusting convection. As I said, this is the first model of convection. So they knew how to represent dry convection and moist convection. They developed a simple scheme known as the convective adjustment scheme. And so at every time they would have the temperature profile going through the convective adjustment scheme. And in this process, they will compute the water vapor mixing ratio at different levels, and relative humidity is fixed. So you can compute the water vapor mixing ratio. And now water vapor is also a greenhouse gas. So they compute how much is the change in the emissivity, mean emissivity and absorptivity, and then compute the radiation change, and the cycle goes on. So this is the flow chart. And they used, for the long wave absorption bands, they used only 4 bands. And they had a rotation band and a 6.3 micron band of water vapor, the 15 micron of carbon dioxide, and 9.6 micron of ozone. And they also had the effect of, because the 15 micron is common to both carbon dioxide and water vapor, they have incorporated this common effect of this common band also. So they use the simple 4 absorption band. And this was another very clever strategy they did. And because I heard a talk by Professor Bjorn Stevens, he gave this problem to his students who use thousands, maybe much more than thousands of radiation bands to compute the absorption. And then they found the results did not change much from what Manbe and Weatherald had done, or Manbe and Strickler had done. And this is the fixed vertical profile of relative humidity that they use based on earlier papers. And they had also assumed different clouds of going high clouds, mid-level clouds, shallow clouds, and they had associated different properties. What is the height of these clouds, what is the amount, what is the albedo, how much they reflect. And so they made the calculations with a clear sky and cloudy sky. And so this is just to give the idea of the spectrum. This is the incoming solar radiation. The maximum radiation intensity is in the visible, and this is the outgoing radiation from the earth. You can see this is and so the maximum is around the 10 micron. And now when you look at the absorbers, now you have the ozone. The ozone has an absorption at the 9.6 micron, which they have considered. And and also they have the absorption of carbon dioxide at the 15 micron band, infrared band. They also have considered the absorption of water vapor at the 6.3 micron and the 15.4. And this was a very clever way of doing this calculation, very strategic. And basically, how they identified, so when you look at the spectrum of the uh, normalized black body curve corresponding to the sun's photosphere, that's about 6000 Kelvin. And this is the black body curve by the Earth at 288 Kelvin. And and if you look at the wavelength, and this is the absorption across different wavelength, basically your thermal infrared is the 4 to 15 micron. This is the region where all the action in the atmosphere happens. The near infrared is at around zero point 0.7 to 4 microns, and the thermal infrared is the band, that is the window where all the complexity of absorption properties or absorption changes in the atmosphere are happening in this band. And if you look at the typical temperatures in the atmosphere for the range of temperatures and the black body emission of the atmospheric temperatures, this is the Planck function. So they very well, we clearly estimated more or less this four band should be good enough. That was their calculation. And with such a simple model, yeah, that's what they did. They estimated what will be the effect of this. If I use this one-dimensional model, if I change the carbon dioxide, how much the temperature of the planet would change. And they earlier, as I said, the paper by Manbe and Stickler, this was in 1964. They had examined the thermal equilibrium of atmosphere with a convective adjustment. First, they looked at the thermal equilibrium. If you had only pure radiation, what will happen? A pure radiative equilibrium. In order to prepare for the study of thermal equilibrium with convective adjustment, calculations were first performed for the simple case of pure radiative equilibrium, and in which pure was approached as an asymptotic steady state problem of an initial value problem. And they also looked at the thermal equilibrium with convective adjustment. So here they have both radiation and convection. Uh, so this is the what they call as a thermal equilibrium. Um, so what they do is, if you have convection, you have to adjust the lapse rate. You have to adjust the vertical profile to a critical lapse rate. And so they used, this is known as the pseudo adiabatic lapse rate, the 6.5 degrees per kilometer. So they adjust whenever the atmosphere becomes unstable, it exceeds the critical lapse rate, they adjust the profile to this pseudo adiabatic lapse rate. Basically, the argument is, it is essentially, the explanation for this fact is rather complicated. It is essentially the result of a balance between the stabilizing effect of the upward heat transport in moist and dry convection on both small and large scales. Basically, they argue that convection tries to stabilize the atmosphere, whereas the radiation is basically has a destabilizing effect. So the radiative cooling tries to destabilize the atmosphere, and the convection tries to stabilize the atmosphere through the transport of heat. And this is the Manabe Strickler paper. What they did was, this is you have a isothermal temperature initially of the atmosphere at 160 Kelvin, is a cold atmosphere, and you also have a warm atmosphere at 360 Kelvin. So they use this radiative convective model, and they keep iterating. Uh, uh, they for several time steps, and this has 18 vertical levels, and time step is about 88 hours. And what they find is, this is the initial initial profile isothermal atmosphere with cold and warm. And after 10 days, the profile, you can see the profile in the troposphere starts, the temperature starts decreasing. And then in the stratosphere at higher level, it starts increasing. And so still it has not reached an equilibrium. This is after 20 days. This is after 40 days. So they keep on doing. And after about 320 days, they reach a kind of equilibrium. So you have a troposphere temperature distribution, I mean, cooling with height, and in the stratosphere, the temperature increasing with height. And very simple calculation from a cold atmosphere. And they repeat this with a warm atmosphere, warm isothermal. And typically, by about 320 days or so, it reaches this kind of equilibrium, thermal equilibrium. And this is from Manbe Strickler paper. How the vertical distribution of the temperature of the atmosphere is achieved in a pure radiative equilibrium and a pure thermal, that is a radiative convective equilibrium they studied. And they say that it takes to reach this equilibrium, it takes about 1 to 2 years from a state of a isothermal atmosphere, whether it is cold or warm, you can reach there. And the important point is that if you have a pure radiative equilibrium, that is only radiation change, the thermal equilibrium has a tropopause at approximately 10 kilometer. For a radiative equilibrium, the tropopause is much lower, 10 kilometer. If you have a radiative and convective equilibrium, the tropopause is higher because of the convection. The tropopause is at 13 kilometer. And importantly, if you look at the surface temperature is warm in a kind of a radiative equilibrium. It is around 332 Kelvin. And if you have a radiative convective atmosphere, the temperature is about 300 Kelvin, much lower. This is clearly saying that this is more like a kind of a desert type of subtropical areas, the desert areas, where the land surface temperature is high, and the atmosphere is basically cooling, radiatively cooling, and the tropopause is much shallower. It's around 10 kilometers. Now, if you come to a region like the monsoon region, or a region like where there is convection, the temperatures are much cooler. Surface temperatures are something like 300 degree Kelvin, but you have very deep convection, and the tropopause height is much deeper. It's around 13 kilometers. And the important point is that, and then they say that for the atmosphere in radiative equilibrium, long wave emission from the ground to the space plays an important role. That means for a desert-like area, if you're looking at the radiative equilibrium, how much radiation is coming from the top of the atmosphere, it's basically the temperature. It is decided essentially by the temperature of the Earth's surface. Now, but when you're looking at a region where there is convection, like monsoon region, the thermal equilibrium, the long wave emission from the atmosphere to the space is very, very important. The long wave emission is going to be determined by the radiation from the atmosphere to the space. This is because it must be substantially contributed by convective heat transport from the ground. That becomes important. And so the scientific questions that Manbe and Weatherald asked was, how much time does it, this is in the 1967 paper, how much time does it take to reach the state of thermal equilibrium when the atmosphere maintains a realistic distribution of relative humidity that is invariant with time? What is the influence of various factors such as solar constant, cloudiness, surface albedo, and distribution of various atmospheric absorbers on the equilibrium temperature of the atmosphere with the realistic distribution of relative humidity? What is the equilibrium temperature of the Earth surface corresponding to realistic values of these factors? And so this is the simple one-dimensional model. And they said that with the fixed relative humidity, this model should satisfy the following requirements. At the top of the atmosphere, the net incoming solar radiation should equal the net outgoing long wave radiation. This is very, very important. You have to have a radiation balance. And this he always insisted, before you do any climate study, make sure that there is a radiation balance between the incoming energy and the outgoing energy. And then the free and forced convection and mixing by the large scale eddies prevent the lapse rate from exceeding a critical lapse rate equal to 6.5 degree per kilometer. This is the convective adjustment scheme which they used. And whenever the critical lapse rate is subcritical, the condition of local radiative equilibrium is satisfied. And they also used a fixed distribution of relative humidity. Yeah. They had a profile, they used observed profile of ozone from the observations. As I said, ozone, you have the status, there's a maximum concentration of ozone in the stratosphere at around 25 kilometers height. And this is what leads to the absorption of the incoming solar radiation, mostly in the ultraviolet. And so these are the experiments they did. With the carbon dioxide concentration, control experiment at 300 parts per million, other experiment where they decreased it to 150, third experiment where they doubled it to 600 parts per million. And when they use the fixed relative humidity, they found that when you compare the control experiment and the double CO2 experiment, the surface temperature increased by about 2.36 degree. And this was with average cloudiness. They also computed under clear sky what would happen. So they could clearly say that whether you have clear sky or the cloudy sky, you can say that the increase in the surface temperature due to the doubling of carbon dioxide they could clearly obtain. And and so there was so this was a very clear demonstration, and also including the effect of the water vapor feedback. And they further argued that this is the picture of if you had only a radiative equilibrium, this the solid line, the atmosphere with fixed relative humidity, the atmosphere, the temperature with height will decrease very quickly with height, and it will have a very shallower tropopause. And whereas if you have a radiative convective equilibrium, the thermal equilibrium with fixed relative humidity, so the temperature it takes longer time to reach an equilibrium, and the temperature slowly decreases with height and in the troposphere, and later on it increases in the stratosphere gradually with height. And this is the radiative convective equilibrium with the fixed relative humidity. But if you have if an atmosphere with fixed absolute humidity and only radiative equilibrium, again the atmosphere will cool very very fast with height, and the tropopause will be shallower. So basically you need convection if you want to get a if you want to get realistically represent the vertical profile of the temperature both in the troposphere and the stratosphere. Convection is very very important. That is the point they said. And water vapor, the fixed relative humidity with the approximation which they used. And this is the effect of the increasing and decreasing the CO2 concentration in the atmosphere. So the surface temperature increases by with fixed relative humidity, average cloudiness by 2.36 degrees. And whereas in the stratosphere, when you double the carbon dioxide, the increase of temperature with height is much lesser than the control experiment. But this is quite contrary to the experiment if you change the solar constant. If you change the solar constant, then the temperature increases. If you increase the solar constant, let us say, the temperature profile in the troposphere increases, and also in the stratosphere it increases. But when on the other hand, if it is due to the carbon dioxide, the temperature increase is seen only at the surface and the troposphere, but not in the stratosphere. Actually, stratosphere there is a slight cooling, in fact. So basically, this is a summary and conclusions of this paper. Generally speaking, this sensitivity of the surface equilibrium temperature upon change of various factors such as solar constant, cloudiness, surface albedo, and CO2 content are almost twice as much for the atmosphere with a given distribution of relative humidity as for that with a given distribution of absolute humidity. So what that means is the speed of approach towards the state of equilibrium is half as much for the atmosphere with a given distribution of relative humidity as for that with a given distribution of absolute humidity. In other words, the time required for radiation condensation relaxation is much longer than that required for just radiation relaxation of the mean atmospheric temperature. And also when you double the carbon dioxide content, there is an increase in the surface temperature by 2.3 degrees centigrade with fixed relative humidity. So these were the important contributions, pioneering contribution of Manbe and Weatherald. And they also did other experiments where they studied the effect of carbon dioxide doubling with a full climate, with a more sophisticated climate model. This was again Manbe in 1975, where they found that if you have a full, not a one-dimensional model, this was a model for basically covering the Atlantic Ocean and the North and South America. They had both land and sea, and with a more complicated three-dimensional general circulation model, where they had transport of heat in the atmosphere, not just the vertical convection, even the lateral transport of heat, both in the atmosphere. And they said that it is shown that CO2 increases, raises the temperature of the model troposphere, whereas it lowers that of the model stratosphere. And the troposphere warming is somewhat larger than expected from a radiative convective equilibrium model. And interestingly, in this paper, they also looked at the effect of the hydrological cycle. What will happen to the hydrological cycle? They suggested that if you double the carbon dioxide, the hydro intensity of the hydrological cycle will become stronger, and which is what we are finding even now. So basically, the areas which are getting precipitation, like the tropical areas, monsoon areas, so the precipitation is going will intensify with climate change, and drier areas like the subtropical deserts, they are going to get drier. So this is basically the intensity of the hydrological cycle is getting stronger, which they have pointed out in 1975. And sorry. And later on, Manabe pioneered development of coupled climate models, not just the atmosphere. They developed ocean atmosphere, land, cryosphere. This was with Kirk, Bryan, Stauffer, how to exchange the fluxes of heat, momentum, fresh water, uh, between the atmosphere and the ocean. So they studied various problems of climate variability and change. So truly a legend. He we can call he is the person who has pioneered coupled climate modeling. The first one, in fact, was started in 1969 by Kirk Bryan. So this is about Professor Manabe. And now let me also cover about Professor Hasselmann. Although I have not very gone through his work carefully, I have, after the Nobel Prizes, I had an opportunity to go through some of his papers, and I'm just summarizing some of his contributions. Basically, he is also a big visionary of climate research. As I said, weather is a chaotic system. This applies not only to extreme events such as storms or heavy rain, but also fundamentally. The German researcher Klaus Hasselmann analyzed this chaos decades ago and thus contributed significantly to our understanding of climate catastrophes. Along with Suki Manabe of the USA and Giorgio Parisi of Italy, Hasselmann received the 2021 Nobel Prize in Physics for the work on chaotic and seemingly random phenomena. Born in Hamburg and for many years director of the Max Planck Institute for Meteorology in his hometown, he showed in the 70s, I will come to this, this is an important paper in 1976, that climate models can be reliable even when the weather is extremely changeable. So this we have to keep, because Lawrence in 1963 had told that there is chaos and predicting weather beyond a certain period is very difficult. So now the question is, there is a question on the credibility. So how reliable are climate models? So can we trust them? So because the weather is changing, is extremely changeable. And that's where the Hasselmann's work contribution comes. The Royal Swedish Academy of Sciences illustrated Hasselmann's achievement with a simile. As a dog on a leash remains in relation to the person who with walks with it, no matter how much the dog zigzags, so too the weather remains in relation to the climate in spite of all the fluctuations. So basically, the weather extremes are basically tied to the climate itself. So as the climate evolves, it is going to dictate how the extreme weather events are going to behave. See, we see the extreme heavy precipitation event, heat waves. These are all extreme weather events. Now, they are clearly linked to the changes in the mean climate itself. So if you are going to alter the mean climate, that has a control on these extremes. That is the main essence he was able to show. And Hasselmann's accomplishments was to develop a stochastic climate model. How he did was by developing a stochastic climate model that translates the fluctuations into reliable statements. And Hasselmann also demonstrated that human influence on climate and warned as early as 1988 that in 30 to 100 years, depending on how much fossil fuel we consume, we will be facing very significant climate change. Climate zones will shift and there will be changes in the precipitation regimes, precipitation patterns, and no longer we'll be able to talk about random results. So this is a very important contribution, and this is the paper by Hasselmann in Tellus in 1976 on the stochastic climate model. This is the abstract of his paper. A stochastic climate a model of climate variability is considered in which slow changes of climate are explained as the integral response to continuous random excitation by short period weather disturbances. Professor Dhar also mentioned about this point about noise, how the noise can get integrated into the signal. This is exactly the problem that Hasselmann was talking, that if you have random excitations, random variation, random pulses in a system, so the integral response, how the random fluctuations can get integrated, um, and how the weather disturbances effect of this random excitation by short period weather disturbances, they can get integrated and they can produce a low frequency spectra. I mean, that is basically the point they're telling. And he showed that the coupled ocean atmosphere cryosphere land system is divided into a rapidly varying weather system, essentially the atmosphere. So the atmosphere variations are happening at a faster rate, that is the weather phenomena, and a slowly responding climate system, that is the ocean, the cryosphere, land vegetation, they happen more slowly. So what they did was in the usual statistical dynamical model, only the average transport effects of the rapidly varying weather components are parameterized in the climate system. So with statistical model, the average, the mean transport of the weather component, they are treated in the climate model, and the resultant is that the prognostic equations of the SDM are deterministic, and climate variability can arise normally only through variable external conditions. So that means if you have a statistical dynamical model and if you are giving the mean transport effect of weather, you will be able to only study the effect of external forcing, and it will be a deterministic problem. But what Hasselmann did was, the essential feature of stochastic climate models is that the non-averaged weather, they are not taking the mean weather, they're taking the non-average weather components are also retained. They formally appear as random forcing. So basically, they appear as random forcing. The weather component is shown as a random weather forcing. The climate system, acting as an integrator of short period excitation, exhibits the same random walk response characteristics as large scale particles interacting with the ensembles of much smaller particles in analogous Brownian motion problem. So it is like a random walk problem which was used for studying the Brownian motion, and the model predicts red variance. That means the low frequency spectra. It predicts the red variance in qualitative agreement with observations. The evolution of the climate probability distribution is described by the Fokker-Planck equation. It's well known in uh, theory for studying the Brownian motion, in which the effect of the random weather excitation is represented by diffusion terms. So clearly, what he showed was what is the connection between climate and weather extremes. That was the problem that Klaus Hasselmann showed. So without stabilizing effect, if you don't, as Manbe used the convection as a means for stabilizing. That is the key in Manabe's work. And here the same idea is coming. Without stabilizing feedback, the stochastic climate model will predict a continuous increase in climate variability. So you will be having continuous variability that will be increasing with time, in analogy with a continuous unbounded dispersion of particles in Brownian motion, uh, and or in a homogeneous turbulent fluid. But stabilizing feedback yields a statistically stationary climate probability distribution with finite degree of climate predictability. So basically, the stabilizing effect is very important if you want to really get a statistically stationary climate probability distribution. That was the idea of this work. And I will not go into the details. And subsequently, he applied this theory. Frank, Frank and Hasselmann, they used this stochastic climate model for studying the sea surface temperature anomalies and thermocline variability. This was in Tellus 1977. The concept of stochastic climate models developed in part one of this series by Hasselmann is applied to investigation of low frequency variability of the upper ocean. It is shown that large scale, long time SST, that is the sea surface temperature anomalies, may be explained naturally as a response of the ocean surface layers to short time scale atmospheric forcing. The white noise spectrum of the atmosphere input produces a red noise spectrum, a red response spectrum, with most of the variance concentrated in longer periods. And this concept later on was applied by Manabe and to study that. So if you have some white noise process like precipitation, which is basically a white noise process, and soil can basically integrate this. Soil has a property to integrate this white noise and produce a low frequency variability. So this was a paper by Manabe and Delworth where they relate to the work of Hasselmann. So they looked at the the temporal variability of soil wetness and its impact on climate. So because many areas you can see there are land areas where the soil can provide an important memory for the climate system, soil moisture. And so what Manabe and Delworth did, this is a paper, they have done several other papers. They looked at the temporal variability of soil wetness, how the soil wetness will vary in time and its interactions with the atmosphere were studied using a general circulation model of the atmosphere. It is found that the time series of soil wetness computed by the model contains substantial amount of low frequencies, variance at low frequency. This is the spectra. This is the spectra. In the x-axis, you have the time, and here the power spectra of rainfall. In the smaller panels are the rainfall and snow melt in different regions, and these big boxes are for the soil moisture. You can see that there is a significant power in the lower frequencies in the soil moisture in different regions, whether it is the subtropics or the tropics. Uh, so there is a significant low frequency variation in the soil moisture. But when you look at the rainfall or snow melt, it is there is you don't get that low frequency signal. It's mostly random. It is a white noise. Now the question is, how does this soil moisture, where does this low frequency spectra come from? And this is where Manabe and Delworth, they use the Hasselmann theory, and they apply the logic from Hasselmann work. Climate variability is influenced by interaction between the atmosphere and its lower boundary. Interactions between the ocean and lower atmosphere have been studied extensively. These interactions may be viewed in the light of stochastic theory of Hasselmann, in which the ocean acts as a long-term integrator of white noise thermal forcing from the atmosphere, thus supplying a long memory red noise component to the atmosphere ocean system. And a similar process may exist over land, whereby the soil acts as an integrator of white noise of the atmospheric forcing, that is precipitation or rainfall, thus supplying long memory red noise component of the atmosphere land surface system. And this is a very novel idea, and my colleagues in IITM, Milind and his colleagues, they are working on this. They are making in situ measurements of soil moisture, rainfall, and trying to understand the soil moisture memory and how these low frequency variations in the soil moisture occur. And actually, Manabe, in his full climate model, they had developed a very simple model of the soil moisture known as the bucket model. That was also a first time they had developed a soil moisture. And then normally, and this, the wetness anomalies in this, it is represented as a first order Markov process, very much similar to what Hasselmann had used. And so what they found was this is a simple first order Markov process of the soil moisture in the GFDL model. So the soil, they have a certain field capacity for the soil layer. It varies region by region, and if the capacity exceeds, if there is excess wetness or excess moisture, that is allowed as runoff. And so this is the equation for the soil wetness equation. And so they computed what is the soil moisture decay time scale, and for different regions of the world. And you can see in the mostly in the mid latitudes and the high latitudes, or Asia and Northern America and the continental areas, the memory soil moisture memory scale is of order of several months. So the soil moisture provides a memory, so it can influence climatic anomalies on the scale of several months. And they did two other experiments by fixing the soil moisture in the. They did long runs of this model, GFDL model, climate model. In one experiment, they fixed the soil moisture to climatological value. In another experiment, they had an interactive soil moisture. And what they found was they looked at the temperature response in the model, and this is the temperature averaged for different latitude. Sorry, for different latitude circles, going from the south pole to the going from the north to the south. Of course, in the southern hemisphere, you have mostly oceanic areas. You don't have many. Don't have land areas. So in the northern, if you see the subtropics and the mid-latitude areas, the temperature variance, what is plotted on the y-axis is the variance of the zonal mean temperature uh, from the two experiments. You get higher variability when you have an interactive soil moisture. So once you have an interactive soil moisture, through this it comes, so you get more variance in the temperature. This happens because of the low frequency variations of the red noise spectra of the soil moisture. I'll not get into the details. And later on, Barnett and Hasselman, they wrote their main contribution, the ideas of the stochastic climate model, which Hasselman developed. They use these ideas to develop how to detect and attribute human-induced climate change, because there are it's not only greenhouse gases that mankind has introduced in the atmosphere. They have also introduced sulfate aerosols uh, due to industries, due to vehicular emissions, also land use, land cover changes. So how do we detect? So we have the observed changes in the temperature and rainfall. Can we detect and attribute how much comes from? Is it because of? And of course there are natural variations like El Nino, like volcanic events, solar irradiance changes. So they are also altering the energy of the atmosphere. So the question is how the changes that we are seeing, whether it is due to human induced climate change, or is it natural. So they developed various techniques, Hasselman and team, and these have been extensively used, how to isolate these different effects of these different forces. And the recent IPCC report has extensively relied on these techniques uh, to bring out the human influence. And these are the assessment. So the recent AR6 assessment report has a very strong attribution. It says that human influence has warmed the climate at a rate that is unprecedented in at least the last 200 years. And in fact, when you see the increase of temperature that you see, the 1.1 degree centigrade, what we have seen in the last century, this is the fastest, and you don't see that in the last 2000 years. And in fact, when you see this has been the warmest multi-century period in more than 100,000 years. So these type of attributions are possible. So thanks to the contributions of Hasselman. And also we are able to separate out natural drivers. As I said, the volcanic eruptions like the Pinatubo, you can see that with only the natural experiments with the volcanic eruptions, you can see these cooling episodes. But if you want to, and they are also seen in the model simulation, which has both natural and anthropogenic forcing. But this overall warming trend, what can be explained only by including the effect of anthropogenic forcing. And so these type of strong attributions are possible. And also it is unequivocal that human influence has warmed not just the atmosphere, also the ocean and land. And the changes are widespread and rapid in the atmosphere, ocean, cryosphere, and biosphere. They have occurred. And as I said, there are multiple drivers. One is the greenhouse gases are trying to warm, but the anthropogenic aerosols like the sulfate, they try to cool. They have partly masked the warming due to GHG has been masked by the aerosols. So these attributions are again coming through the detection attribution techniques developed by Hasselman. I mean, the theory of which developed by Hasselman found provided the basic foundation for these techniques. So basically, the observed temperature change, that is temperature increase during 2010 to 2019 relative to 1850 to 900 is 1900 is about 1.1 degree. And if you had an experiment only with models that were running only greenhouse gases, the warming would have been around 1.5 degrees. And if you have both greenhouse gases, natural aerosols, anthropogenic aerosols, the combined, then this would be around 1.1. And the aerosols, especially the sulfate, they are leading to a cooling of about minus zero point 0.4. So these individual different drivers we are able to separate out. So the attribution problem is possible, and it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere has occurred. And there's also a strong regional attribution. Climate change is already affecting every region on Earth in multiple ways. And Klaus Hasselmann had developed theories even for how to do regionally, how to attribute. And the changes we experience will further increase with warming. And of course, unless there are rapid and large scale reductions in greenhouse gases, limiting the warming to 1.5 degree will be beyond reach. So these are some very strong statements from the IPCC. And in the future, these I just thought I will give one example of a future projection. If you want to make, in the past we know how these different drivers have changed, how carbon dioxide has changed, how aerosols have changed. So we can run all these models and climate models and make understand the historical changes and attribute. But what about the future? Future normally we all these climate model groups, they follow certain protocols. Um, so we all run the same experiments known as the in the AR6 they are known as the CVIP6, they are known as the shared socio-economic pathways. So depending on what kind of mitigation and adaptation strategy you use, what kind of, whether you're following a very sustainable approach or whether a highly fossil fuel development approach, the concentrations of the greenhouse gases in the atmosphere are going to change. So there are different scenarios, and so I'm just giving you some example, especially this scenario, the one shown in yellow, SSP 245. I'm particularly drawing your attention to that because by end of the 21st century, this scenario, the concentration of the atmosphere, greenhouse carbon dioxide in the atmosphere is going to be double if you go to the SSP 245. And there are some very high emission scenarios. I'm not going into that because Manbe's paper was about doubling of CO2. So if you go to the SSP 245, by end of the 21st century, the this is the bestest long-term warming during 2081 to 2100. In most of this is from multi models in the same from the IPCC report. The best estimate is around 2.7, and if you have multiple models, the range is going from 2.1 to 2.3 to 3.5, depending on various feedbacks in the models. It varies from model to model, so you have a very likely range between this. And the best estimate is 2.7, not very far from what Manbe said about 2.36. And in the near term, that is 2021 to 2040, it's about 1.5. And the midterm, 2040 to 2060, is about 2 degrees. And interestingly, our own model from IITM, this is the first climate model from India, our projection for 2081 to 2100 is 2.3. It happens to coincide very nicely with what Manbe and Weatherald had shown. So again, when we look at the range from what Hasselman had shown, even the extremes, when you look at the changes in the weather, they are going to be tightly linked to the way the climate itself is going to behave. That is going to constrain the weather changes. And so it's important to have a probabilistic view of how the change in the climate will happen under different scenarios are likely to happen. And as I said, I was very fortunate to be associated with Professor Manabe in Japan. I worked at the Frontier Research System for Global Change. These are some nice pictures I thought of sharing. And this is during an award ceremony in 2000 when I had the Frontier Award. This is another legend, Professor Taro Matsuno, who was our Director General. He made huge contributions in tropical meteorology, in the wave dynamics, in the tropical processes, and you can see this is Professor Manabe here, Professor Matsuno, and my colleagues Dr. Swadhin Behra, Saji from India. So there was a big contingent from India at that time in Japan, and basically I was working in the global warming group headed by Professor Manabe. My group leader, I was hosted by Professor Masato Suki, a very nice person. I was working with him. We wrote several papers. This was during our farewell ceremony. I was returning back to India, and this is with my family, my wife, and my son. This was on the day we were leaving Japan. So you can see, very simple man. And our son Bharat, he actually is also a student of IISER Pune. And this is in Professor Manabe's office. You can see this very nice poster of a picture of this is a hanging of a dinosaur. He used to be fascinated with all these dinosaurs and paleoclimate. He used to talk about how the glacials, interglacials, ice ages happened, and how the dinosaurs, with during the periods of deglaciations, how they became extinct, and so on. Yeah, and no, during the period of warm periods, how different dinosaurs survived. And so he was very much interested in knowing those things. And I had an opportunity to visit Princeton in 2004. This was at his home. With This is Mrs. Manabe. So great human being, great legend. And so thank you very much for your kind attention.
Thank you, sir, for the wonderful talk.
Thank you. I'm sorry I took a little more time.
Yes, that's okay.